Welcome, James Freitag from Berkeley, and to tell us how to count solutions to differential equations.
Yeah, and so I changed the title so that it's just so it matches Marcus's title, although I mean something different. I literally mean counting solutions. I mean a finite number. Okay.
It's not an insult.
No. It's just an amusement. Okay. So, okay, I'm not going to review most of differential algebra, but here's the basic problem that I think anybody can understand. You're given some collection of differential polynomials over some differential field K with a distinguished set of derivations delta, and I always assume K's characteristic 0 and delta commute. Delta is a finite set of commuting derivations. And I'll just write x even though it could be in many variables or whatever. Okay. And so the first question, which I expect you could probably answer in multiple ways, is how can you tell when and so I'll write V of this collection for the common 0 set of those differential polynomials, and I'll think of the solutions being in any differential field extension, but if you're familiar with this subject, you know you just need to look really in some large differentially closed field. But I'm interested in when the set of solutions to some collection is finite. Okay, and then assuming that collection is finite, I want to bound this size. Okay, and so this may sound like a trivial problem. In some ways it is, of course, because there is just a bound, of course, which doesn't have anything to do with the particular coefficients of the equations or anything like that. You can prove the existence of that bound, you know, just by fairly elementary things involved in first-order logic. Okay, model completeness of DCF and things like that. Okay. That's not what I'm interested in, though, because I want to know the actual numbers. Okay, so I want to know the actual size, and there are reasons why I want to know that, and I'll try to explain the reasons. Okay, but for the most part, I'll concentrate on explaining how you come to this, and it's an algorithmic process in a way, although the algorithm is exceptionally simple and sort of thinking about making sure that the algorithm works is really the bit. There's only 3 steps in the algorithm. Okay, so I just don't know the answers to these questions, but more or less if people consider this problem, it seems like a foundational problem in differential algebra, although I don't really know if it's been considered that closely. And of course, I already asked this question, but I think it's not. And so the reason that I think it's not trivial is that if you could just sort of straight away solve this problem in a fairly automatic way, well, you'd be able to solve some interesting problems in number theory. Let's put it that way. Okay. So here's a simple example, and there's a wide variety of examples that you could make up like this. Okay. So if A is a simple abelian variety which doesn't descend to Q, and all that means is that A is some abelian variety which isn't defined over Q and is not isomorphic to one defined over Q. Then I'll let this set, which I'll call A sharp, be the Coltrane closure of the torsion points of A. And it's true that this is a finite dimensional differential algebraic group. Some people call it the Manning kernel. And a lot of applications of sort of model theory of differential algebra to special points conjectures have been around this set. Of course, like work of Buyum, Rashofsky, and people after them. Okay, so now take a curve, and you'll have to. So in general, if your assumptions are different, you need to state things a little more complicated. But the way I've stated it, it's fine. This set is finite. So I mean an algebraic curve. So this set is finite, and it's complicated, but it's well understood what the actual equations here are. And the way that you get effective finiteness results around, around these function field versions of Manin-Mumford type and Mordell-Lang type conjectures is by literally doing what I suggested on the previous slide, by showing that the set of solutions to a collection of differential equations is finite, and then showing how finite it is. Okay, so that is literally what Reshofsky and later some other people did, and also this has been carried out in slightly other circumstances as well. Okay, yeah, so these are complicated, so complicated that when they've been written down several times incorrectly, but no. Okay, so here's another reason why I think it's, so that's just the ordinary case. So here's another reason why I think it's a non-trivial problem. So this is a quote of Johnson, who worked on something sort of similar to this, or something that felt similar to this. And so the gist of this quote is that Johnson says, okay, you have some collection of differential equations and partial differential equations. And it often happens that only by differentiating can you see new relations of low order somehow. Okay, and so this is, I think, it's pretty understood that this sort of phenomenon exists.
Well, it was long before Johnson. It's just
yeah, of course. But somehow Johnson formalized this and in a certain sense and proved things about things like bounds on how many times you'd have to differentiate for arbitrary differential algebraic varieties and things like that. So,
regularity paper.
But is this a notion of evolution? What you're talking about?
No, I mean, let me just give an example, and maybe you'll see what I mean. Okay, here's a system of differential equations, and so I'm looking for solutions in the variable y, and the variable x is a parameter, which is for which delta 2 of x equals 1. Okay, that's my setup here, and okay, so what are the set of solutions to this equation? Just y equals 0, and the way you can see that is just by doing what Johnson says here. Okay, and so I don't know. This is just my way of saying I think this problem will be harder in the partial differential case in general than in the ordinary case.
But this procedure has nothing. I mean, it's long before Johnson. So you differentiate. It's like,
There's
nothing to do with.
I mean, I know about it with Johnson's assumptions, but it's okay if it came before. I'm not saying that this is original. Okay, all right. Okay, so all right, so let's move on, since quotes of Johnson are troublesome. All right. So here's how I would solve this problem. Okay, maybe you would solve it a different way. I would bound the number of times that you have to differentiate in some way. And then I would try to recast the problem in terms of certain components of, let's say, truncated arc spaces of algebraic varieties. I'll explain what that means. And then I would run an algorithm where the operations in the algorithm, since this is easier for me, only involve operations on algebraic varieties, not any operations on differential algebraic varieties. And then I would keep track while I'm running that algorithm of the degrees of the things which appeared using just like sort of basic intersection theory. And then at the end, if I end with a finite set, what will happen is that finite set will be bounded by the degree of a certain variety which appears. Okay, so I'm just going to say what happens. We'll go into the specifics in a minute. Okay, so how does that work? So I want to use the following notation, which is pretty, okay, so this approach is standard at least amongst model theorists and people doing differential algebra, say in the style of Boolean. If you take an affine algebraic variety and then consider W a subvariety of this set, so I'm taking the Zariski closure, I'll write CL for Zariski closure, of V and its image under delta. And if, okay, so I don't want to go into, I don't want to explain all this functorially, I don't want to explain this as a scheme, but if you just think of V as synonymous with its U points for some very large differentially closed field U, then it's literally the closure over some small subfield K of this graph. Okay, so then, well, you can write, so a slight typo here because I just differentiated once. If L is 1 there, then this is what I mean, but otherwise I mean differentiate X bar multiple times. So you write a differential equation in terms of a pair of algebraic varieties. So this is nothing complicated, of course, but there are some nice aspects to it, especially when, say, you know.
So W should have an index L, is that correct?
Well, it's just an algebraic variety, but in terms of where W lives,
Yeah.
it will live in some higher affine space. It will live in this affine space here.
How do you define delta V?
Pardon me?
How do you define delta V?
Yeah, so that's what I said. I'll think of, I mean, look, there are ways to do this functorially or scheme theoretically or something else, but it'll take a little while to explain, so I'll prefer to do it this way. I'll think of V as synonymous with its solutions in some large differentially closed field U. Okay, so this is literally a set. Okay, a set of things in affine n space over U. Okay, and so when I write delta V, I literally just mean the image of the elements in this set under the map, delta applied to each coordinate. Does that make sense?
Differentiate every
coordinate.
Is it a prolongation?
Yes.
Sure. You could call it that, yeah, if you like.
But it only takes not the whole.
You can call it that, although
The whole thing is
It takes a direct product and then
it's more than that. It's more than that. So you can have an A, and then hit delta B, and then the delta square C, you know, in that set.
Oh.
So prolongation would be A, delta
Oh,
A,
I'm
delta
sorry.
square A. and
I realize the problem there. There's a typo. I don't mean the
Okay, all right. You mean comma? You mean comma?
Yeah.
yeah,
Tuple.
I mean those to be
You mean
commas.
tuple?
Yeah,
Okay.
right, yeah.
I'm sorry. Sorry.
Another question about notation. Your
Sorry about that.
your W seems to want L many.
Yeah, I said that as well. This is another typo.
Oh, sorry.
In
Okay.
fact, yeah. So W should live up here, not just in A to N
Okay.
in general.
Okay.
And so the thing that in it
So
should
it's
be
wrong.
X, del X, del X,
Yeah. This is not exactly what most people have called prolongations in the literature, but it's something similar. I'll explain the relation.
Yes.
Okay. So this set is irreducible in the Colchin topology, or in the Zariski topology. It's not trivial to see, but you can use the Colchin irreducibility.
What do you mean by affine algebraic variety?
I mean a zero set of some K polynomials.
Is it just
No, varieties are irreducible.
Because it intersects out.
So here it comes a hidden assumption, it's not pronounced.
Well, depends what you think about varieties, but I think they're irreducible.
Right.
But one question is, so it is a fact that sorry, I've written V delta when I mean BL of V. This set BL of V, it will almost, okay, I mean, if your variety V has singularities, BL of V won't usually be a complete intersection, even if V is. So determining the actual generators, the ideal of polynomials which vanish on BL of V would in general be somewhat difficult. Okay. So So in other words, for the sort of intersection theory that I'm going to be doing, I'm going to have a need to know the degree of this guy here in terms of the degree of V. And so I don't know a way to just do that directly in an easy manner. Neither did the people who considered this question first. So, so Reshofsky and Play answered this question in the ordinary case, but unfortunately their proof is wrong because there's a claim which is actually incorrect, but they didn't prove that claim. It's usually how it goes. Sorry, it should be BL of V. And so their approach basically relies on knowing that this BL of V is a component of some other certain algebraic variety whose degree we do understand. And I'm going to explain why that's actually true. Okay. So there's a kind of variety or kind of scheme that geometers studied a lot more than what I call BL of V. And I call it the mth arc space, although if you look in sort of literature on geometry, this might be called the mth jet space sometimes. Although that terminology is troublesome because some other people mean other things are jet spaces. But what I mean is that the mth arc space is a scheme which represents the T mod T to the m+1 points of the original variety V. Okay. So, it's a definition, but you can actually write down generally.
So you're saying it's a functor?
Yeah, it's a functor. Yeah, yeah, it's a functor from schemes to schemes. It doesn't exist for an arbitrary scheme, but certainly for varieties, and certainly for varieties it exists.
Is your K algebra finally generated?
Yeah. So for varieties. Okay. For variety, I mean integral, separated, finite type. And it's a fact that the degree of the mth arc space is just the product m times the degree of V. And so if you could show that so it's also clear when you begin doing things that that you have a containment here. Okay. But so if you could show that this was a component of this, then you'd be in business because you could, so there's well-known ways to bound the degree. Okay? But the problem is that in general, this guy here will be reducible. So this is some closed subset of some larger affine space, which is very often reducible. And the other problem is that it's also not usually equidimensional. And the codimension of this inside of this can be arbitrarily large. So you'll have to think of how to show that it's a component. I mean, there's some thought there. And that's the missing part of the Reshofsky-Pillay proof. So Reshofsky and Pillay claimed that this guy here was of a certain dimension, and that's just not true. So they have this. Okay, so it's true that when V is smooth, the fibers above any point A on V are just affine spaces of some predictable dimension here. Okay? But it's not true when you start with a variety that isn't smooth. Okay, so
Jim, I have a question.
Yes.
So how are they related to two objects? First, if you take the radical differential ideal generated by the equations and plot it at the point n, or if you take your equations, differentiate them up to order n, and take the radical ideal of that.
Okay, so
you get varieties in each of the cases. So how are they related to the varieties that you have here?
Yeah. So so those varieties that you're saying are going to be more close, are going to be, so probably what you said, I have to make sure, probably what you said, maybe if you generate the whole differential radical ideal and then you just look at the part of order less than or equal to m.
Yeah, that's one.
Yeah, that should be Bm of V.
That's Bm.
Yeah.
Okay, so then.
But this is something different. Yeah, this arc space, because somehow when you go, okay, so what you're really doing when you generate the whole differential radical ideal in some ways is you're taking a certain direct limit of rings. You could think of it that way. Or in terms of these guys here, you're taking the inverse limit of the
Whatever,
VMs.
that is just formality. What do you do with equations?
Yeah, so those equations will imply the equations for these arc spaces.
Yes, so the second variety that I suggested.
Yeah.
That you take original equations and just differentiate them up to order n. And consider that variety. How is different from this?
But not take the radical.
Well, take the radical algebraic ideal.
They are different.
Oh, okay. They could. I think they could in general be a little different. Yeah.
I think the first one you said is the B and B.
Yeah.
The second one is the arc space, which is also called the prolongation. So James arc space, that's really what was usually called prolongation.
That's what, and is that what I
The
said?
second one.
The second one.
You can take the derivatives of x and then take the derivatives of variables and take that series.
Yeah.
Okay, that's precisely. So you don't have to introduce all the formalism, which is very simple.
Well,
you do equations up to order n.
Let's see.
Yes,
So what's the? Yeah.
Okay, so look, the reason I'm doing this is that there's a whole theory developed by algebraic geometers and developed by Musa and Scanlon of these arc spaces here, these truncated arcs, and you can use those. You can use that theory to prove that BL is a component of VM. Okay. So you have to do, okay, you need to do some things. Of course, this only works if V is defined over the constants, because, you know, if you think about what's going on here, when you formed this variety here, you really were treating V as if it were defined over the constant field. But there's a similar operation which is more complicated that I'm not going to describe, and that's not true. And, I mean, there's even this fact, which I won't go into. Okay,
But
maybe
is it one derivation? I forgot. Is this one derivation or?
yeah, right now one derivation, but of course all this works for multiple derivations. You just need to set things up a little different. Okay, and okay, I think in the interest of time, there's been a few questions. I'm not going to sketch the proof of that, but I mean, the proof that I would do basically uses, basically the strategy is to prove that there's only one component of the prolongation which surjects dominantly onto the base, and then calculate the dimension of that component using things like generic smoothness.
X is not the same as V?
Sorry, X is the same as V. And you calculate the dimension using things like generic smoothness, and then get bound, and then show that it's a component, and then get a degree bound. Okay. And all this is pertinent because there's certain what model theorists call geometric axioms for differentially closed fields, and you can state them. In this way. Okay. So if you have a differentially closed field, then whenever W is an irreducible subvariety of this variety Bm of X, which projects dominantly onto X, then you can take any Zariski open subset here, U of the base, and you can find an A so that should be nabla M of A is in U. And so in particular, that would give you infinitely many solutions to that differential equation, because you have a lot of freedom to choose open subsets away from any finite set of elements. Okay, so So now the algorithm itself, or the strategy, is, I think, at least somewhat clear. Okay? You check, basically, if this W projects dominantly onto the base. And if it doesn't project dominantly onto the base, then you do something. And if it does, you're done, and you just have to check if V is a finite dimensional variety, which is easy. So check if...
Question from Alice.
Yeah.
How do you know what M to use?
How do you know what M to use? Well, in the ordinary case, you could set up everything with M equals 1 all the time. But in the partial case, that's the main obstacle. Okay, so, and I won't get to that at all because I'm going to be out of time in a minute or two. So go to step, so if it's not dense, then replace it with, in here, when I write pi 1 of W, I don't mean the constructible set, I mean the closure of the image, I mean the scheme theoretic image. And so you replace V with the projection of W into the coordinates of V, and then replace W with W intersect this prolongation, as some people are calling it, of V. Okay? And now you've reduced the dimension of those varieties, and now go back to step 1. But the algorithm, it can't go on very long because no theory-anity. And I told you how to calculate the degrees of things, and you know Bézou's theorem, so you know how to calculate degrees of intersections as well. So you keep track of the degrees, and then if the solution set ends up being finite, well, then you get to step 3, and you calculate that finite number. And so let me just say, if you think about this, what happens is that you get that bound, which is actually the same bound as Reshkovsky and Flay established. It's just that their proof is missing some steps. And of course, like I said, complications arise in the partial case. It seems like people understand this phenomenon pretty well. But the essential problem is to bound the t in which you have to work in bt of v, because as t gets larger, so does the degree, and so you need to have a handle on how big t can possibly be, and maybe there's other ways to do this. Our solution to this sort of followed some pretty recent work of David Pierce, in order to solve this problem, you have to solve a purely combinatorial problem, which sort of has to do with orderly rankings, if you think about it correctly. So, okay, so, well, here's the theorem. I don't want to explain everything because I think I'm pretty much out of time.
1 minute more.
Okay, 1 minute. Okay, so you more or less do this. You more or less do the same process, and if you go back to this, the essential thing is to formulate some sort of principle like this, because this principle here is just completely wrong in the partial case, because of this Johnson-like phenomenon. Okay, or this phenomenon of detecting lower order equations only after you differentiate. Okay, I mean, I learned it from a paper of Johnson. I'm not claiming it's original. And but the essential thing is to know how far you have to differentiate in some way. Maybe there are other solutions to this problem, and maybe they'd be better than the bound we calculate. And so, yeah, I just have a few comments on the bound. So, I mean, there's an interest in improving the bounds if you could. So, in many function field cases of conjectures in Diophantine geometry, this technique is really the only way that there are effective results. Okay, so if you improve the bound, you would improve various finiteness bounds related to number theoretic problems. Okay? I mean, you could just read off the better bound and then substitute in that particular situation. but I don't know a better bound. There are worse bounds. So the original formulation of this problem ended up coming up with much worse bounds, although it was maybe 25 years ago now due to Boolean. So, and I don't know any, I mean, let me know if you have suggestions for some applications of the partial version of the theorem. There are some conjectural Diophantine results there, but I don't know. I don't know if that's actually true. So I'll end there. Thanks.
Thank you very much. More questions? Comments? Okay, so thank you.
Well, I have maybe a very naive question. I don't understand the setup of counting the number of equations because you set some boundary or initial values, because differential equation and an ordinary differential equation will always have infinitely many solutions. So in which sense you
No, so yeah, okay, so that's true if you wrote down some equations that you really understood. But I mean, look, okay, so write down, think of the sort of example that I'm giving. Write down your favorite simple abelian variety which doesn't descend to Q, and then write down the equation for a curve on it. No, I know it's a joke. I know it's a joke. But
an example from a different area.
Yeah.
But
no, I understand that.
Come up with a system of PDEs that has.
yes, it's inconsistent.
No, consistent, but has finitely many
Yeah, like the
solutions.
one you gave at first, the second slide. It was
Yeah, of course. In PDEs, the phenomenon is more troublesome. I mean, yeah, of course, in ordinary differential equations, when you write down a differential equation, it's fairly easy to see whether there's going to be infinitely many solutions or not. But, okay, under normal circumstances. But that's not true, for instance, for the differential equations, say, satisfied by certain number theoretic objects, like the torsion points on an abelian variety, or like the analytic J function. I mean, so it's like a third order nonlinear differential equation. I mean, look, here's an example. I mean, the J function satisfies a third order equation. Now, suppose that you wanted to look. So I'm taking the J function on each coordinate. Sorry. Now, suppose that you wanted to impose some sort of algebraic relations on the images over here. Well, I mean, that's more or less what things like the André-Oort conjecture are about. And if you just take some arbitrary algebraic curve over here, the number of transcendental points, so that J of A1 and J of A2 fly on that curve, ends up being a finite set. But I don't think that it's easy to just tell by staring at the differential equations. Or at least it didn't seem to be easier. Those people would have just proved the André-Oort conjecture that way. So, I think examples are a bit difficult to give in the ordinary case.
Okay, thank you very much. Very interesting talk.